Hey, so today we're going to tackle a real classic, a problem from a physics book that has stumped students for ages. It seems so simple, right? It's just a thrown ball. But I promise you, hiding inside its graceful arc is a secret about rotation that's going to make you see motion in a whole new way.
So let's just get right to the heart of it. This is the question that trips everybody up. When you hear angular momentum, you probably think of a spinning planet or a gyroscope, something that's actually rotating. But what if I told you that a ball, thrown perfectly without any spin, still has angular momentum? How on earth is that possible? Well, it turns out the secret is in what we think angular momentum is versus what it actually is.
All right, so our journey starts with a problem from the legendary IE Irodov. We're going to break down problem 1.186, which, on the surface, looks like any other projectile motion problem. But it's got a fantastic little twist.
Okay, let's look at the wording here, because in physics, the details are everything. Two phrases are absolutely critical. First, angular momentum vector, which is a big hint that direction matters. But the real kicker is this part, relative to the point from which the ball is thrown. That phrase right there, that's the key that unlocks the entire problem. It's all about our point of view.
So, before we can solve anything, we have to get our definitions straight. Let's really nail down what angular momentum is, especially for a single particle that isn't even spinning. This is the key to the whole thing.
So read that definition carefully. Notice it says nothing about the object having to rotate on its own axis. It's all about the relationship between two things, its position and its momentum, all viewed from one specific point. Think of it less as the momentum of a spinning thing and more as the momentum of motion around a point. That's the big idea.
And this little formula is where all of the action happens. M equals R cross P. Now, R is just a vector pointing from our starting point out to the ball. You can think of it like a lever arm. And P is just the good old linear momentum, mass times velocity. That little x in the middle isn't your normal multiplication. It's a cross product. It's a special operation that measures how much of a turning effect these two vectors have with respect to our origin.
Now listen up, because this is where people get tangled. Here are the big traps to avoid. Number one, angular momentum is not the same as linear momentum. Number two, it's a vector. The direction is just as important as the number. And number three, and this is the most important one for our problem, it all depends on where you're looking from. If we had picked a different origin point, we would get a completely different answer. It is all relative.
Okay, we've got our concept and our formula. Now we just need the raw data. To figure out the angular momentum, we first have to perfectly describe the ball's flight using the basics of kinematics.
Now, this stuff should look pretty familiar, right? This is Kinematics 101. These equations tell us exactly where the ball is, both horizontally and vertically, and how fast it's going in each direction at any given moment in time. This is the information we need to build our R and P vectors.
So all we're doing here is getting organized. We're taking those equations we just saw and packing them neatly into the components of our position vector, R, and our momentum vector, P. See how it's all laid out? Now we have everything we need to finally do the cross product.
Okay, the prep work is over. It's time for the main event. We're going to plug our vectors into the cross product formula, and the math is going to reveal the answer to this whole mystery. Now, the good news is that for motion that's just happening in a 2D plane, like on our screen, the cross product formula gets a lot simpler. It just boils down to this. You take the x position times the y momentum and subtract the y position times the x momentum. And that k at the end, that just tells us the resulting vector is pointing either straight out of the screen or straight into it. So we take all the pieces from our table and we plug them into that formula. Now, I'll spare you the algebra, but trust me, some terms cancel out really beautifully, and we're left with this elegant result. This is our answer, and look at what it tells us. First, the angular momentum gets bigger and bigger over time, and it grows with time squared. And that negative sign, it tells us the vector is pointing into the screen, which represents a clockwise rotation from our starting point. So that was part one. We have a general formula. Now for part two, let's get specific. The problem asks us to find the angular momentum at the very highest point of the throw using some actual numbers. All right, here's the data the problem gives us: the mass, the angle, and the initial speed. But wait a second, our formula needs t, the time. So the question we have to answer first is, how long does it take for the ball to get to the very top of its arc? Well, just think about what's happening. At the very peak of its flight, for just an instant, the ball isn't moving up or down. Its vertical velocity is 0. And that is the physical key we need. We can just take our equation for vertical velocity, set it to 0, and solve for t. Easy as that.
So we take that time, we plug it back into our main equation for angular momentum, we pop in all the given numbers for mass, angle, and velocity, and when we crunch the numbers, we get our final answer. The magnitude of the angular momentum at the apex is 7.3 kilogram-meters squared per second.
Okay, great. We've got the number, we solved the problem. But in physics, the number is only half the story. The real goal is to understand why. Why is there any angular momentum at all? And why does it change over time? Well, it turns out the culprit is a force we know very, very well.
And that force creates something called torque. The best way to think about torque is that it's the rotational version of force, right? Just like a force, a push, or a pull changes an object's straight-line momentum, a torque, a twist, is what changes its angular momentum.
And this right here, this is the beautiful connection. The rate of change of angular momentum, that's dm by dt, is literally equal to the torque. And for our ball, what's the only force acting on it after it's thrown? Gravity. So as the ball's position r changes, the torque that gravity creates around our starting point also changes. And it's that changing torque that makes the angular momentum change. It all fits together perfectly.
So this is the big takeaway. This is the answer to the puzzle from the beginning. A non-spinning ball has angular momentum because a force, in this case gravity, is creating a torque on it relative to our chosen origin. That's it. That's the whole secret.
So let's end by scaling this idea way up. Think about our solar system. Could you pick a point in space, not the sun, and find that the sun's gravity is actually creating a torque on a planet relative to that point? What would that mean for the planet's angular momentum? It's pretty incredible that a simple problem about a thrown ball gives us the tools to think about the grand dance of the cosmos. Thanks for working through this one with me.